Graph the pair of parametric equations in the rectangular coordinate system. We're given x equals 2t and y equals t plus 5, and we're giving a domain for t is -2 is less than or equal to t is less than or equal to 3. So I'm going to plot points, but I need 3 columns, so t will give me x and y, and I'm going to start at -2 for t because that's where t starts, and I'm going to go -1 and 0 and 1 and 2 and 3. This might not be enough. I might be able to go to decimals or fractions to get more information, but I think this will be enough. Let's find out. So if t equals -2, we plug that into the x equals 2t, and then we get -4. We plug -2 into the t plus 5, and we get 3. Make sure you're taking the t values and plugging them in to the formula for the x and the formula for the y. I missed out a bit. And then evaluate. Okay, next, if t equals -1, -1 times 2 is -2, and -1 plus 5 is 4. If t equals 0, 2 times 0 is 0, 0 plus 5 is 5. If t equals 1, 2 times 1 is 2, and 1 plus 5 is 6. If t equals 2, we get 4 and 7. By this time you should probably see some patterns like 3, 4, 5, 6, 7. No guess there. That's going to be 8. -4, -2, 0, 2, 4. That's going to be 6. So you can usually, when you're done, take a look at the patterns and see if you made a mistake. Just nice. Now what we need to do is we need to actually be plotting just the x and the y. So we have a list of 6 points. Let's put them down. -4, 3. -4 on the x, up 3 on the y. We start at this point. -2, 4. Pretty close. 0, 5. 2, 6. 4, 7. And 5, and let's see, 6, 8. Straight line. So we then connect the dots. Don't go beyond there. Don't put an arrow at the end of it. You can put an arrow in the middle to signify the direction this thing is moving, but it starts at this dot and it stops at this dot, and it does not go further. We have a line segment. This domain restriction from -2 to 3 limits this, otherwise would be a line forever in both directions, to just this segment. Alright, that's it. Okay, graph the following parametric curve in the rectangular coordinate system. So I'm going to start off with a t, x, y chart. T, x, and y. And t goes from 0 to 4, so I'll use 0, 1, 2, 3, and 4. Alright, we'll start off with 0. I'm going to take the 0 and I'm going to plug it in for the t in the x and get 0 squared is 0. And I'm going to plug the 0 in to the y and get square root of 0, which is also 0. With 1 squared is 1. Oh, I've messed up. Let's see, y equals square root of t plus 5. Aha. So, oh, my eraser is not working. Try again. There we go. So let's try this one more time. If t equals 0, 0 square root of 0 plus 5 is 5. The y variable is 5. Now with 1 squared is 1, square root of 1 is 1, plus 5 is 6. 2 squared is 4, square root of 2 plus 5 is messy, but we could calculate it. 3 squared is 9, square root of 3 plus 5 is messy. 4 squared is 16, square root of 4 is 2 plus 5 is 7. So that one works out pretty well. And I probably won't even need my calculator because we're going from 5 to 6 to slowly to 7. Won't be too hard to graph. But let's find out. We'll start off with the point 0, 5. 0, 5. This is our initial point. 1, 6. The next nice one is 16, 7. So I'm going to jump to 16, 7. 15, 16, 7. What we're getting, we have an x squared and a square root. We're getting this shape. It's a parabola shape. It's a y squared parabola. It's going in that direction. But it does stop there and it does start there. The other points you could plot in there, and that would be fine. Their square roots are a little messy, but they are dots in there as well. Now the shape, this is off of this parabola, y squared parabola, but we only have that top section. That's it. That's all there is to it. Next question. Graph the following parametric curve. X equals 3 tangent t and y equals 5 secant t. We're given a domain for t 0 less than or equal to t less than or equal to 2 pi. So I'm going to draw a t, x, y graph, t chart, t, x, and y, and 0 to 2 pi, so 0. Let's start at 0. Tangent 0 is 0 times 3 is 0. X is 0. Secant of 0, cosine of 0 is 1, secant is 1, 5 times 1 is 5. So we're starting out at the point 0, 5. That's our initial point. Now, cosine, secant, tangent. I'm going to jump a little bit, and maybe this isn't a good idea. Let's find out. Let's see, where's tangent undefined? Pi halves? Something weird's going to happen at pi halves. X is undefined, and y is undefined. So we have an interesting phenomenon happening. Although they're giving us the domain is from 0 to 2 pi, we can't use all those values. So let's go to pi. I believe we can use pi. Tangent of pi is 0 times 3 is 0. Secant of pi is negative 1 times 5 is negative 5. So we have this point down here as well. See, I think I put that in the wrong spot. 1, 2, 3, 4, 5. I put it at 6. Silly. Let's put it at 5. There we go. So we need to do more values than just these. So let's try pi sixths, pi fourths, pi thirds to get an idea of what these look like. Pi sixths. Tangent of pi sixths is 1 over the square root of 3. Times 3 is 3 over the square root of 3. Secant of pi sixths is 2 over square root of 3 times 5 is 10 over square root of 3. We can evaluate that, approximate it with our calculator. Pi fourths. Tangent of pi fourths is 1 times 3 is 3. This is a good one. Secant of pi fourths is square root of 2 times 5 is 5 square root of 2. Pi thirds. Pi thirds, tangent of pi thirds is square root of 3 times 3 is 3 square root of 3. Secant of pi thirds is 2. 2 times 5 is 10. So some of that works out. We can now go and approximate these. So let's take a look at these. So at pi sixths, 3 over square root of 3 is approximately 1.73, so about 2. And then it's up 5.2, so about 2, up 5.2. This thing's not growing too fast. Then over 3, and up about 7. And then over 5-ish, and up 10. Now, from symmetry, etc., we're actually getting, it looks like a hyperbola out of all this. So there's still a lot more to plug in and figure out on this one, and that's okay. You just have to work it out and keep plugging it in, and this is kind of a long problem to actually graph with the TXY chart. It would be likely easier to do a substitution, figure out, eliminate the variable t, and let's see what this one looks like if we do it that way. Give us an idea of maybe another way to approach this problem. So let's start off by copying these down. X equals 3 tangent t, comma, y equals 5 secant t. And tangents and secants. I know an equation with tangents and secants. I hope you do as well. It is tangent squared theta plus 1 equals secant squared theta. This is one of the Pythagorean identities. So from our equations, I can get tangent t equals x over 3, and I can get secant t to equal y over 5. I'm going to just plug these in. So tangent t, instead of theta, it's t squared. We have x over 3. That's tangent squared plus 1. I'm making these strange pluses tonight. Excuse me. Plus 1 equals, and secant squared, 5 y over 5. Okay, so we have x squared over 9 plus 1 equals y squared over 25. And this would be y squared over 25 minus x squared over 9 equals 1. This is a hyperbola that opens in the y direction. So this gives you another technique that you might be able to get the curve that you need. Now, if I go back to our graph, we did get this picture going on, so it's going in this direction. So I'd actually want to go and erase the equals. Oh, I can't do it now, it's way too. So it's going down, it's going in this direction. And we'd have to figure out the other one by picking out, I imagine this part happened in quadrant 1 values, so this is probably quadrant 2, quadrant 3, quadrant 4, that kind of thing. So a lot of work to plot, but this is what it would take to do one of these. Alright, great. Eliminate the parameter of the pair of parametric equations. Say that 10 times fast. So let's start off by just doing a substitution. T equals x minus 4. Well, y equals t squared, but we know that t is x minus 4, so y equals x minus 4 squared, and that is all there is to this problem. So we're essentially eliminating t, so you solve for t and plug it in. And if you have a y equals, like we do here in the second one, y equals, it's nice to substitute into that, so you end up with a y equals in function notation and don't have to do any other kind of solving in the problem. Excellent. Write a pair of parametric equations that will produce the indicated graph. The line segment starting at -4, 4 with t equals 0, so at times 0, and ending at -13, -11 with t equals 3. Let's get a picture of this. The points have very negative values, so I'm going to write our xy chart, our xy graph, more like this rather than the regular one. -4, 4, and -4, 8, 12, 13, -11, down about here. So we want to actually go this direction. T equals 0, t equals 3. Okay, so we need to figure out what happens to the x variable and what happens to the y variable. The parametric equations are x equals something of time and y equals function of time. Alright, so here we are at -4. -4, and we have to get to -13. How far is from -4 to -13? That's 9. So totally, we have to go -9 in the x direction. Because we have to do it in 3 seconds, 0 to 3, we can nicely divide this up and have 3 seconds. So we have to go -3, then -3, then -3. If we go -3 each second, we will go from -4, first second, to -7, -10, -13. Okay, great. So our x value, we're starting at -4 and we're subtracting 3t. Each time we go -3. Okay, let's see if this works out equivalently the other direction. We are at 4 and we have to go to -11. How far is that? That's 15. We have to go down 15 totally. But we have to do it in 3 seconds. So if we go down 5 each second, we'll go from 4 to -11 in 3 seconds. So the y value, we're starting at 4 and we're subtracting 5 each second. So combining that with our 0 less than or equal to t less than or equal to 3, we have a really nice, simple, logical approach to finding parametric equations of line segments. You could also think of this as mx plus b. So mx plus b. b is the starting value, so that's where you start off. So this is the starting value for x, this is the starting value for y. And these are slopes. Okay, how do we find the slopes? So the slope of the x variable is x2 minus x1 over time. Actually t2 minus t1. And that would give us -13 minus -4 over 3 minus 0. And that is -9 over 3. And that's how we can get the -3. So you can actually work these -3's and -5's out with the slope formula. But make sure it's x and t, and m sub y would be y2 minus y1 over t2 minus t1. Slope formula works fine, and I think that the logical approach makes sense, especially because it worked out so nicely. If these hadn't been nice whole numbers, then I would definitely go to the slope notation. Okay, mx plus b, line segments, and make sure to give your domain for x. Excellent. Solve the problem. A projectile is fired with an initial velocity of 600 feet per second at an angle of 45 degrees with the horizontal. In how many seconds will the projectile strike the ground? Round your answer to the nearest tenth of a second. The parametric equations for the path of the projectile are given as x equals 600 cosine 45 degrees t and y equals 600 sine 45 degrees times t minus 16t squared. Now the x variable has nothing to do with this problem. The y variable is the vertical component of this projectile. The ground, it just depends on how high up it goes, how long it'll be before it hits the ground. So this question is not asking how far away from the cliff it's fired or whatever. It's just when's it going to hit the ground. So essentially, ground, y equals 0. That's really what this problem is. So we're going to set the ground, the y equals 0. So we have 0 equals parentheses 600 sine 45 degrees t minus 16t squared. Solve this equation. Ooh, it looks quadratic. Looks like it's going to be a mess. Quadratic formula until you realize there's two terms and t is common. So we can factor out the greatest common factor, t times 600 sine 45 degrees minus 16t. So therefore, t must equal 0, or 600 sine 45 degrees minus 16t must equal 0. This is just simple solving equation with the zero factor property from Math 1010 or earlier. Now t equals 0. That's when this thing started. Yes, the projectile was at the ground when you fired it. That doesn't help us. But this other one is a positive value. If we solve for t, we'll get negative 16t equals negative 600 sine 45 degrees. So t would be negative 600 sine 45 degrees divided by negative 16. and calculate that. Make sure you're in degree mode in your calculator, and because of the instructions of round your answer to the nearest tenth of a second, we get to 26.5 seconds. And that is how long it takes for this projectile to hit the ground. The parametric equations for projectile motion is very nice because if you realize that because of gravity, the y value, the height, is decreasing as a squared minus 16t squared. And the x one, though, is constant. It's just continuing to move to the right. Now this is without any air resistance. So is y without any air resistance. But because different things happen, the gravity only works vertically. If you break up your parametric equations so that you have the horizontal and vertical components, then gravity only affects one of those. All right, that completes this problem.